Now we're continuing on 7.6 in the book, which is lecture number 27. And we're going to do example problem 748 as kind of a demonstration of what we're going to do once we find the angular velocity, omega, as a vector, and the angular acceleration as a vector. I mean, usually we're finding these because we want to find the angular velocity and or we want to find the linear velocity and the linear acceleration, and this is an example of how to do this. All right, so let's look at this system here. All right, I've redrawn it because I needed a little more space than there was on the lecture handout. So imagine you have some disk here, and it's spinning with some angular velocity p, and it has some radius r. And what we want to find is the velocity of this point A. But it's attached to this fork here, which is spinning with angular velocity omega 1, which is also attached to this system here, which is spinning with angular velocity omega 2. So now how do we think about this problem? And it's a little bit different because if you look at this disk, right, there's no fixed axis that this disk is rotating about because it's moving in this way because of this, this way, the negative z because of this omega. It's moving kind of around this way, but then also it's rotating about this axis. So there's a lot of rotations going on here. And because you can't point to some place on this disk that's going to be fixed, we want to think about a rotating coordinate system. And now if you remember when we had our formula sheet, right, we already have a formula for rotating axes here. And it's always been here at the bottom. We're going to have our sum VA equals VB, omega cross R plus VREL. And these are all bold because they're all vectors. But before that, we were always thinking of omega as just in the k direction. But now in these problems, omega can have components in multiple directions. So we need to find a coordinate system and think about how it's rotating. So that's always the first step to these problems. Step 1, we're going to identify our coordinate systems. Sorry, I'm going to get this right. All right. So here, and the problem already sort of had drawn a capital X, which I've kind of emphasized with these marks, a capital Y, and a capital Z, and those are going to be fixed. So XYZ coordinate system is fixed. But now there's a lowercase x, a lowercase y, and a lowercase z coordinate system. And I think we're going to find this most convenient to think about that as fixed to this piece here. I'm going to kind of fill it in orange. So this piece that's rotating with both omega 1 and omega 2, but not with p. And the reason is because now this piece will have this fixed point here. So we can think about this as rotating with some omega net. All right, so the XYZ coordinate system rotates with some omega, which I'm going to try to color code with blue. We're going to have some omega equals omega 2 in the j direction. And now this j axis here is this fixed, capital J for the capital X, Y, Z. And it's also rotating with omega 1 in the I axis. And now the I axis is here, but this axis is in fact rotating. All right. So now we have, we know how this is rotating. We know what its angular velocity is. We could even sort of draw this, right? It's going to be positive in the j and negative in the I, so it's going to be kind of off in this way. But this vector itself, the angular velocity vector, will be changing because things are rotating. So we can draw that as the alpha vector. And when we think about how it's rotating, because it's rotating like this, we can draw, and there's an equation in the book, but I always kind of have to think it through, like which is this rotating about, right? So this whole reference frame here is going to be changing with this. And so that's why I kind of drew this in this direction, because it will be rotating out into the, like towards me, away from the paper. And so we're going to have omega 2 in the j hat direction crossed with omega 1 in the I hat direction. And here, for the method that's recommended by the book, where we're going to use the formulas, you can take this cross product, because at this instant, j and I are going to be perpendicular to each other. So that gives us k. And we don't have to worry about the fact that, like, this is a capital J and this is a lowercase I, because at this instant, the ij, like x, y, and z lowercase, are in the same directions as x, y, and z uppercase. So that's why we can take these cross products, because we're not planning on taking the derivative of this. All right, so now we find the velocity. That's step 2. And so we're going to use this equation, and we could have picked some other point here, like alternatively we could have said VA equals VO here, and then had some vector from O to R, but I think it's a little bit more intuitive if we use VB. So VA equals VB plus omega cross R from B to A plus VREL. And so here we're going to be using, for this omega, it's the rotation of the coordinate system that we care about. And what's this VREL? If we were in class, I would ask and have you wait to think about this answer. But this relative velocity is going to be the velocity due to this rotation, right? So this is rotating in the frame that rotates with this orange bar. And then VB is just how this B is moving in the negative z direction because of omega 2, right? So that's the only thing that's causing VB, or point B, to move. So we've got, and we can do that with cross products. Omega 2 in the j cross BI, where B is this distance here in the I direction. And then we want to add that to omega of the coordinate system crossed with R from B to A. And so the omega of the coordinate system is just this omega here, that's a vector. And now R is going to be R in the j hat direction at this instant. And then the relative velocity here is going to be the component due to this rotation P, which is in the k direction. You want to make sure you get your signs right. I think you're using the right hand rule here. So omega 2, if you curl your fingers here, that's in the positive j. And omega 1, if you curl your fingers, right, like that would be in the opposite of x. So that's why this is negative. All right, so we're taking these cross products, and now we're all set. We've laid everything out, and all we have to do is take these cross products, and we got j cross I is going to be negative k. We got j cross j. Oh, we don't have to worry about that term. Nice. So then we got I cross j is going to be positive k, but there's a negative sign here. And then we've got k cross j, so that's going to be negative I. So here we put that down here. And you may want to kind of keep remembering that this term is actually VB, and just like we expected, it's in the negative z direction because omega 2 is rotating that. Even like draw VB here. And then that in the negative k, also omega r is the 1r. Yeah, so like this omega here is causing this to rotate backwards. So it's gonna, see if we can bring that back in focus here. There. So we've got this going backwards here. And then we also have our relative velocity, which is going to be in the negative I direction. So that's going to be here, in the negative I direction. So we've got these three components of our velocity. All right, so then step 3, we want to find acceleration. And it's important that you don't want to throw away your velocity terms here. So because, as you see, that otherwise you're going to have a lot of cross products. So we're going to have acceleration of point B plus omega cross R plus alpha cross R plus 2 omega cross VREL. plus AREL. And now, oh look, we can actually reuse VREL. We don't have to recalculate that cross product. And similarly, this omega cross R term is going to be the same as this omega cross R term. So we can build on our velocity expression. All right, so here's our acceleration of point B, and I kind of drew another little diagram here. So acceleration of point B is going to be inward, right, because it has some omega, and this is actually omega 2. I forgot that too. So omega 2 here, and that's in the negative I hat direction here. And then we're going to have omega cross R, so that's going to be, so this is our omega R, and then we're going to cross that again with the same omega that I put in blue, so that's just this that we calculated for our system. All right, and now we've got our angular velocity, which we calculated. Here it is in red, and that is what we calculated up here, our angular velocity as well. All right, and we're going to cross that with Rj. And then we have that 2 omega cross VREL. So we can take VREL from up here, and we can just take that same angular velocity of our rotating coordinate system, and we take that cross product. And then finally we have AREL, which just like VREL is from that P, we're just going to have a P squared term. So that fifth term is pointing down like this. Right, so we just take these cross products and group them in by which direction. So this is going to be in the I direction. We've got a J cross K, so that's going to be in the I direction as well. And we've got a K, an I cross K, so that's going to be J. KJ, that's going to be another I term. And then here, we don't have to worry about this because it's cross I, but we do have this component. So that's going to be in the K direction, and then we have this in the J. So when you add up and get the signs right, you will get the correct answer here. And so the trick to doing it this way is being careful with your cross products, being careful with the definition. Your choice of coordinate system is real important. So you want to choose a coordinate system that that rotates about some fixed point. And then sometimes, I mean, if this was a real problem, you could even have like another rotating thing happening on here, and you can like stack up these rotating coordinate systems on top of each other. So like in that case, like this relative term could have its own relative velocity, and so on and so forth. I think the problems for this class, we won't get too deep into that, but if you did find yourself defining extra coordinate systems, that still works. You can still get the right answer. It just may take a few extra steps. So now you may be wondering, I know that velocity and acceleration, they should be just derivatives of position vectors. Why can't I just take some vector here, b in the I direction, and then plus r in the r hat direction, and start taking derivatives of this? You absolutely can, but it's actually a bit more involved. So let's just take a look at what that would look like from the beginning. All right, so you'd have to define r hat in some other coordinate system, like I'm going to call it J3, since we already have a capital J and a lowercase j, and it would be, at this point, aligned with J3, but it rotates with some omega, and so and it rotates with our regular omega, but also J3 would rotate with some p, and so you could define J3 as equal to the cosine of beta j hat plus sine beta I hat. Right, so now you would be converting J3 into I and J coordinate system. And the reason we would need that, we'll see if I'll show you a little bit. And then we would also want to be thinking about, okay, so this J that we're talking about as our in our rotation matrix, we'd also want to convert that into the lowercase ijk coordinate frame. And so you'd want to have there would be some components, right? So you would have your j, and you could kind of draw a little sketch like this, where like the capital is like this and the lowercase are like this, and after some time, like whenever there was some rotation, you would have these components of big J in little I and little j, or actually little k and little j, right? With some cosine here, where this would be the theta would be 0 at this instant, but the theta dot term would show up, because then when you would take these cross products for velocity, because you'd be trying to deal with everything here, you would have to take that into account, because now this cross product, you wouldn't want to just do that, because the cross product itself could be changing over time. So then you need to take the derivative of that cross product, which would mean you would need, before you take the cross products, you would need to have everything in these components. This would be if you just want to like crank it through and take time derivatives of things, right? And not use these formulas. And I'm happy to answer more questions about that if you guys request an example in the discussions.